So in this video, I want to demonstrate the 1702 EPROM programmer I've designed for my Altair 8800 computer. You can see the printed circuit board here. At the moment, this is Rev 1.05 of the board. There's a couple of things to point out here. First off, you'll see the yellow wrap wire on the face of the board here. I had an issue with the port decoder for the ports the board lives on that was addressing the board incorrectly, and this fixed that. I also had a couple of inverters accidentally left in a couple of addresses over here, and so those pins are bent out on this IC, and they're just jumpered across. This is a 1704 inverter. I've added a bleeder resistor up here on the big filter cap. That cap charged up to about 80 volts for the programmer, and without the bleeder resistor it took forever to discharge. Boy, that solder joint looks lousy. There's a 50 volt AC transformer that's hooked up here. You can see it here in the background a little bit. That's providing 50 volts AC rectified to about 80 volts DC, and then goes through a voltage regulator circuit here. The other two things you may notice is these two footprints appear empty, and that's because the MJE702 and MJE708, or there's an 802 and a 702, sorry, are mounted to the back side of the PC board, and that's because the footprint I used had pins. Actually, the component layout, the part I used in KiCad had pins 1 and 3 swapped, and that resulted in the base and I believe the collector being swapped. So just by flipping the parts around and putting them in, did the correct pin out. There's of course a textile socket up here to put the 1702 in. There's a voltage or a variable resistor here that's used to set the 47 volts for programming. There's a couple test points on here. There's this black lead flopping around here. If I ground that lead, it enables the high voltage into the circuit, and that way I can hit the test points and calibrate the voltages. The board works by consuming 4 ports on the Altair bus. The base port that the board decodes is a latch to latch data to the EPROM right here. Port +1 is to latch the address to program the EPROM to. Writing or reading to base +2 will generate a programming pulse that starts the circuit doing its thing, and then I can check on the programming status on port base +3. Board works by a series of counters. There's a 555 timer that generates the initial pulse at 33.3 kilohertz. When the programming pulse happens, these counters start counting and they sequence the things that have to happen on the board. So there's various pulses that get sent at 47 volts and 59 volts. There's some odd programming voltages here. As the circuit runs, and I'm relying completely on the counter chain here to generate those pulses. There's a couple of LEDs here. This one's been removed in the final design. This one just tells you that the programmer's active. So we've kind of looked through the board. So we've taken a quick look at the programmer hardware. Let's take a look at the little MBasic program I've written to drive it. So my goal here is to program the Altmon into 1702 ROMs. On the FTC Plus controller card, I have the Alt ROM and the upper 2 KB of memory. And these two little, these variables here get set to the beginning address of each one of those 256 byte blocks. But I said 256K a second ago, 256 byte blocks. So the programmer, as we talked about, has a base port address that's strapped to be 192 decimal. So that base port, if we write to it, will latch the data to be written to the 1702. Base +1, the address. Base +2 triggers a programming sequence, and if we read from base +3, we can get back the programming status, so we can wait for the hardware to be completed. We're going to loop over the 256 addresses to the source data. We're going to go to 170, which is the program loop. We're going to latch the data to be written out to that base port. We're going to latch the address here out to the base port +1. Got a little subroutine here that basically zero fills hex values written to the screen, so I want to output the address in hex zero filled and the data in hex zero filled here on the line. We're going to print a caret. I'm going to make sure right here the programmer isn't already active. It'll just lock up here if the programmer for some reason is free running. We send the program start pulse. We wait for the program cycle to end. And we've got a little loop here that'll just keep looping, and every 4 iterations it'll put a period to the screen. Then go back to 290, and this will just loop here until the programming sequence is done. We get down to 320, where we print out the done and we return. We go back to the loop, and we continue programming. And this is just a little stub program or subroutine that takes the value in TP and says if it's less than 16, put out a leading 0, because I hate the fact that hex string does not put leading zeros. So, with that said, let's go ahead and load up a 1702. Get one in the socket here. Now there is 80 volts DC active on the back of the board here, so I do need to be careful with my fingers. I need to edit line 130. Because I want this to be the first ROM, and that's F800. I'm going to change this to an 8, and that'll pick up 256 bytes for the first 1702 I want to program. And let's let this go loose. And here we go, and we should now see the programming LED start to blink on the programmer. You can see the programming running. So each time the LEDs blink here, it is programming 1 byte. In the EPROM, it takes multiple pulses to program, with the voltages being flung around to weird values. 1702 erases to all zeros. We're programming in 1s. And this will just crank away here. It's going to take a bit to get through one ROM. They don't program very fast. The second LED over here indicates the high voltage is on. There's a separate V-enable signal that turns the high voltage on, and I removed that in the final design because it's redundant. It basically echoes what's happening on the programming active LED over here. At this point, we just let it keep running. Like you saw there, this is an M-Basic program driving with a card on my Altair 8800, or Altair 8800, I seem to say it wrong a lot, CPM 22. So we're getting there. The board does not have the ability to read the ROM back to validate it, so this is a write-only board. The assumption being you have another card you want to put the ROM into, and you can validate it in that card. In this case, I've spun up this little card here. It'll hold 8 1702s. This is based on the wire-wrapped card we looked at quite some time ago and designed. This is just that same card on a PCB. I used this card here to learn KiCad. It was my first KiCad project, and the programmer was my second KiCad project. You know, besides schematic errors I made, you know, leaving a couple inverters in and just not getting the port decoding exactly correct for the program pulse, you know, and the footprint issues, the card actually came together pretty well. I've done some changes, and what will be the final card were completed. So let's go ahead and pull that EPROM out. Programmed. This one's labeled for position 9, and we'll program one more here on camera. I need to edit 130. And change this to a 9. Run the programmer again. The same sequence happens here. So say this programmer is my second design. I like having the old school wire wrapped board in the machine if I can spot it here without knocking the camera around too much. I really do like this card that we wire wrapped, and this may actually be the card I actually leave in the machine. Again, there's position there for 8 1702As. Just because I like the fact that it's wire wrapped, it's very vintage. You've seen this card before. Another thing to note here is all of the components on this programmer were available in the mid to late 70s. There's all the transistors, the semiconductors, everything on here, the ICs were all available then. So there's nothing modern about this design at all. From the 555, the TTL logic, the 28212s, the latch address and data, it's just all very much from the era. And we're still chugging along. Say not a lot to see here besides blinking LEDs and my Altair front panel way off there in the background. We're coming up on 9 minutes into this piece to program 2 ROMs. Like I say, it's not fast. I'll only demonstrate these first 2. I may actually take the challenge of programming, writing a little programmer in like Aztec C that you could potentially like send an Intel hex file to, something like that. I got to think about it. We're done. Really, I wrote this specifically to program, or designed this to program these 8 1702s and then whatever I might need to in the future. Anyhow, I think that wraps up this demonstration part of this video, and we'll talk soon.